All right, we are tasked to integrate or find an antiderivative for the integral of w to the ninth power times the square root of w to the fifth minus 1 dw. So, as I mentioned in the previous video, the best guess is if you don't have an obvious choice for you just hope for the best. Choose something and hope for the best. You'll notice that a great first step, at least, is to just, if you have a square root, just grab the entire thing that's under a square root and call that u and see where it leads you. Notice I'm certainly not saying that that's always going to work, but what I'm going to do is grab this thing under the square root, call it u, and hope for the best. So let's do that. I'm going to let u equal w to the fifth power minus 1. That implies that du is the same thing as 5 times w to the fourth power dw, right? Okay, so you might say something along the lines of, well, shoot, I don't have a 5w to the fourth. I don't have a 5w to the fourth. Notice I have 5w to the fourth right here. I don't have one in the integrand, but I would say this. Keep going and see if something will turn out for you, because what I do think I have is, well, first of all, I'm going to divide both sides by 5, so to speak here. 1/5 du is the same thing as w to the fourth dw. Notice this. If u is the same thing as w to the fifth minus 1, that implies that u plus 1 is the same thing as w to the fifth power. All right, so notice that I can rewrite this integral as the integral from w, or I don't have any bounds, but I have the integral I keep wanting to say from something to something. The integral of, I'll start with w to the fifth power times times the square root of w to the fifth minus 1. And, oh shoot, I'm missing a w to the fourth, so let me put it right here. Oh shoot, guys, check this out. I have w to the fourth dw sitting right here. I have u, which is w minus 1, sitting right here. And I have w to the fifth sitting right here. So I think based on everything I have, w to the fifth is the same thing as u plus 1. W to the fifth minus 1 was our original substitution. That's the same thing as u. And w to the fourth power dw is, of course, the same thing as 1/5 du. So how does this integral transform? We don't have to worry about bounds in this case. This is the same thing as the integral of u plus 1 times the square root of u times 1/5 du. Again, so to make sure all colors line up, this u on the inside of the square root is sitting right here. I have a 1/5 du, that's this guy right here. Everything is properly transformed. Okay, very nice. Of course, this is the same thing as 1/5, using our integral rules, times the integral of, here, I'll do this kind of quickly. That is the same thing as u times the square root of u plus the square root of u du. All right, notice all I did was the distributive property on these two guys. I also grabbed this 1/5 and took it outside the integral. That's basic integral laws. This is the same thing, knowing our exponent rules. Notice I have not done any calculus yet. Really, I haven't done any calculus. Oh, shoot. Yes, I have. Step from here to here was indeed calculus. But besides that, everything is algebra. Most of calculus, you'll recognize, is algebra. That might have been a contradiction, but who knows? This is the same thing as the integral of u to the 3/2, knowing our exponent rules, plus u to the 1/2 du. And of course, this is the same thing. Of course, this asks a question. What function has u to the 3/2 plus u to the 1/2 as its derivative? Okay, what function with respect to u has that as its derivative? Undoing the power rule, I think I know that that function is going to be the same thing as 2/5 times u to the 5/2 plus 2 times u to the, nope, that's wrong. Let me try again. Plus 2/3 u to the 3/2. plus c. Of course, notice that I am not attributing that to the fundamental theorem of calculus because that's not the fundamental theorem of calculus. This is simply me anti-differentiating. This is me asking this question. What function has this as a derivative? Okay, simplifying, this is the same thing as let me use the distributive property correctly. 2 25ths times u to the 5 halves plus 2 15ths times u to the 3 halves plus, I'll call this c star. Notice it's not the same thing as c because I just multiplied it by 1/5. Back substituting. My original substitution was u is the same thing as w to the 5th minus 1. Okay, so back substituting, what I will get is 2 25ths times w to the 5th minus 1 to the 5 halves plus 2 15ths times w to the 5th minus 1 to the 3 halves plus this magical constant of integration, c star. Done. I back substituted, fully integrated. Moving on to the next example. Okay, geez. Gosh, we're not holding back here. All right, example 2. Okay, let me try this. What you might be tempted to do, and I'm almost tempted to do this inside the video, is, like I said in the previous example, just let u be this entire thing under the square root. But I think you'll quickly notice that that's not too helpful, or is it? Actually, you know what? Let's try it. I mean, why not? And again, it might be the case, I haven't done these yet, it might be the case that we go to a brick wall and we come to a screeching halt with this substitution. I would honestly, so there's a few ways to differentiate this. Some of y'all are probably yelling, okay, the quotient rule, and that'll certainly work, but what I'm going to do is add 0 just because I think that's fun. So this is the same thing as 1 minus 2 over x plus 1. And to find the derivative, 1 is going to delete, correct? And what I will have is 2 divided by... this is not going to work. 2 divided by x plus 1 squared. Is it going to work? Should I hold out hope? I don't think that's going to work. All right, so bad substitution. I don't think it's going to work because I don't see an x plus 1 squared anywhere, and I don't see how I can generate it. So let's try something else. Very often, there's a sneaky way you can crush these U-substitutions. Sometimes, like I say, with a U-substitution, you want to find both a function and its derivative somewhere in the integrand, and sometimes you don't get both of those. Sometimes you only get one of them. For instance, what I'm noticing right here is I see a 1 over x squared. That is the derivative of a famous function, and that's going to be negative 1 over x. So what you could do, well, first of all, I'm actually going to ignore the negative. I'm going to simply let u equal 1 over x and hope for the best. Why? Because I see its derivative right here. Again, I don't see 1 over x anywhere. Actually, I really can see 1 over x. I can force 1 over x to show up right here, which is kind of the key. Yeah. To see what's going on, what you could do is force factor out a 1 over x here, or excuse me, force factor out an x here, and you'll see a relationship. Okay, but I'm not gonna attack this too many different ways. Like I said, I see the derivative, or up to a constant multiple, of 1 over x sitting right here. So I think that gives me a hint for a nice choice of a U-substitution. And to be clear here, you guys, there's many different ways to make a U-substitution. So as I make this choice, you should not think to yourself, this is the only correct U-substitution or substitution. There are likely many other ways to do this, but and I encourage you to try them, but this is the one I'm going to choose. this tells me that du is the same thing as negative 1 over x squared dx. And of course, that tells me that negative du is the same thing as 1 over x squared dx. And check this out. I have this piece right here. Notice I don't have a 1 over x anywhere, but I think immediately, for free, this does tell me that x is the same thing as 1 over u. So how can this transform? Every time I see an x here, I can replace it. Oh, let me go back to full screen here. So every time I see an x here, I can replace it with 1 over u. And of course, I have this 1 over x squared dx that I can replace with this piece, negative du, right here in the integral. So let's see how this is going to transform. Let me get the right color. Okay, here we go. This is the same thing as the integral of the square root of 1 over u minus 1 divided by 1 over u plus 1 times the negative du. Okay, so to be super clear here, maybe I'll color code this. X is the same thing as 1 over u, and I see x here and x here. That was replaced with 1 over u. And I have this negative du right here, and that is the relationship given right here, okay? I don't know why I changed colors randomly, but you get the idea, hopefully. All right, so how does this transform? This is the same thing as the negative integral. Well, I'm going to simplify fractions. It looks like what I got is the square root of 1 minus u divided by 1 plus u du. Okay, and that is the same thing. Okay, tricky integral, but I think do we have a trick? Oh my gosh, this is a great integral. All right, I'm kind of just fell in love a little bit, you guys. Watch this go. This is the same thing as the square root of 1 minus u over 1 plus u times 1 du. All right, mathematicians, they don't ever stop doing this, by the way. Mathematicians don't ever stop multiplying by 1 or adding 0. They do it all the time. I've literally done it like 3 times in this video so far. I'm going to multiply by 1, but I'm going to multiply by a fancy version of 1. This is the same thing as the negative of the integral of the square root of 1 minus u divided by 1 plus u times the square root of 1 minus u divided by the square root of 1 minus u du. And through simplifying, multiplying square roots, this is the same thing as simply 1 minus u divided by the square root of 1 minus u squared du. All right, so why was that savage? Originally, I had no idea how to integrate this. But all of a sudden, I think I can split this integral into 2 different fully computable integrals. So watch this. This is the same thing. I'll be careful here with the negative. As the negative of the integral of 1 divided by the square root of 1 minus u squared du minus the integral of u divided by the square root of 1 minus u squared du. Okay. Now, if you didn't see that, maybe I'll put an intermediate step. Sorry, you guys. That was kind of a lot. Okay, so what I just did was I rewrote the inside. That was not any sort of calculus. That was simply, well, it was a little bit of calculus, but it was, first of all, adding fractions. I rewrote the inside as 1 over the square root of 1 minus u squared minus u divided by the square root of 1 minus u squared. Close the parentheses, du, right? And that got me right here because the integral of a difference is the difference of integrals, and we've made it to this step right here. Check this out, you guys. This integral, I ask myself, hey, what function has this as its derivative? And then I immediately recognize, well, maybe not immediately, I think. I go through my memory banks and go, okay, 1 over 1 minus something squared. What function kind of looks like that? Oh, I know, sine inverse. So this is the same thing, let me get the right color, as the negative of sine inverse of u. Okay. And then maybe I'll do a little bit of a quick exploration on why I don't have to include a constant every time, but I will do that this time. So let me call this constant C1, right? And then on this one, I still have this minus the integral of u over the square root of 1 minus u squared du. And I look at what my original variable is. It was x, and I made a substitution, sorry, right here, u. So I've already used x and u, but what I'm immediately noticing on this next integral is I need to make another substitution. So what I'm going to do is let, could literally be anything. Let's go with b be equal to 1 minus u squared, all right? Again, perhaps you don't see that quite yet, but you might go through a few trial runs on what you should substitute. This is going to end up working. Why? Because when I take the derivative, I will have negative 2u, and notice I have a u in my numerator. So I can employ this substitution, and I can make a nice transformation of this integral right here. This implies that the derivative of b is the same thing as negative 2u du, and that, of course, tells me that negative 1/2 of db is the same thing as u du, and look at what we have. In yellow here, I have a u du, and I made this nice substitution with b, so I see that right here. This is the same thing as b, and both of these combined give me negative 1/2 db. All right. So how does that transform things? This will be the same thing as the negative of sine inverse of u plus c1 minus the integral. I'll show all steps of, so that numerator is going to be negative 1/2. And I want to leave the db here. I want to leave the db for after the integral. So I'll write db divided by, well, that's just going to be the square root of b, right? So this combined with this is the yellow part. That's easy enough. So this is the same thing as here. I can use the distributive property. This is negative sine inverse of u minus c1 plus, or actually, it's going to be minus. Okay, let me explain this. This negative is going to distribute to this guy, but then I'll have an extra negative right here, so it's going to be minus. Let me get that. Minus 1/2 of the integral of 1 over the square root of b db. All right. All right, so that is the same thing as negative arcsine of u minus c1 minus 1/2. Okay, so let's anti-differentiate this. I'll go a little bit quickly. That's just going to be 2 times the square root of b plus, I'll call it c2. All right. Now it's substitution world. First of all, I know that b is the same thing as 1 minus u squared. All right, so let me substitute that. So this will be sine inverse of u minus c1 minus, oh, this is kind of nice, minus the square root of b minus 1/2 c2, right? I should have just done the substitution there. Okay, so negative sine inverse of u minus c1 minus the square root of 1 minus u squared. Okay, so what did I do? I recalled that b was the same thing as 1 minus u squared. Then I have minus 1/2 c2. I'm going to bunch these up. This is the same thing as negative sine inverse of u minus the square root of 1 minus u squared. Okay? And then here's what I have. Here's what I'm going to write. I'm going to write plus negative c1 minus 1/2 c2. And then I'm just going to make an observation that that's just another number, right? Negative c1 minus 1/2 c2, that's simply an arithmetic combination of 2 different numbers. So let's just call that c. And of course, the last substitution I'm going to do, my original substitution way at the beginning was u is the same thing as 1 over x. Making that substitution one more time. This one was fun. Negative sine inverse of 1 over x minus the square root of... Actually, let me simplify this a little bit. Check my work here, but I'm pretty sure that's going to be the same thing as the square root of... Oh, shoot. 1 over x squared minus 1 over x plus c. All right, there you go. Nice, adorable little answer there. All right, let's try another one. Okay, famous type of integral that we need to be able to deal with here. This will be a little bit of a journey, so buckle in. This will take a little bit of time, but I'll try to go slowly and explain all steps. My first observation is I want to do division on this integrand. I want to simplify this as much as possible before I dive in and integrate. Always do algebra before your calculus steps. So what I'm going to do is rewrite this. I'm going to rewrite this as the integral. You know what I'm going to do? I'm just going to rewrite this denominator in the numerator, just for fun. Now, you guys should be yelling at me through your laptop screens. X squared plus 5x minus 3 is certainly not the same thing as x squared minus 6x plus 16. So, you know what? Let me pause and fix that. Originally, I had negative 6x, or excuse me, originally I had 5x. All of a sudden, I have negative 6x. So let me just fix that by adding 11x. Okay, so make sure you catch that. Negative 6x plus 11x is indeed the same thing as 5x. Hence, I really do all of a sudden have an x squared and 5x. X squared sitting right here, and 5x sitting right there. Then I can just play that game again. Check this out. Originally, I had negative 3. All of a sudden, I have plus 16. Oh, shoot. Let me fix that. All right. Hopefully, that's picking up on people. It's hard to know if I'm speaking at you through a computer screen. But why was that so useful? Why did I do that? Check it out. This is the same thing as the integral of x squared minus 6x plus 16 all divided by x squared minus 6x plus 16 plus 11x minus 19 all divided by x squared minus 6x plus 16. Close parentheses, dx. Okay, so that's simply adding fractions, but look at how helpful that is. Now we have the integral of 1 plus 11x minus 19, all divided by x squared minus 6x plus 16. All right, that is certainly super easy to anti-differentiate. Now I kind of have reduced my issue to this thing right here. Perhaps the best way to do this is to force the derivative of the denominator. Okay, so let me say this again. Force the derivative of the denominator to show up in the numerator, all right? So, big issue. When I take the derivative of the denominator right here, what I'm going to get is a 2x minus 6, and that's it. So, that's going to be a 2x minus 6. Notice I don't have that in my numerator. So what I could do is simply force it to show up. Watch that. Watch this happen. This is the same thing as the integral of 1 plus 2x minus 6 all right. So far I am certainly lying to you. All of a sudden I have a 2x right here when originally I had an 11x, all right? So let me fix that by multiplying this by 11 halves. All right, so look at what I just did. If I multiply this thing right here by 11 halves, then through the distributive property, I'll have 11 halves times 2. 2's cancel, giving me 11x. Oh, shoot, that's exactly what I had at the beginning. All right. Now, of course, I'm certainly not done yet. When I multiply through this 11 halves to this negative 6, I'm going to get negative 66 halves, or negative 33, and I certainly do not originally have negative 33. So you know what? What I'm going to do is simply add 33. All right, so to make sure you are picking up on what I just did, when I distribute this 11 halves to this negative 6, what I will get is negative 33, but I don't have negative 33. I have negative 19. So what I'm going to first do is add back that 33. And then, of course, this, so the 11 halves times the negative 6, and this 33 will amount to 0, and I still need that negative 19, so I'll place that right here. All right, so look at what I have all of a sudden. This is the same thing as the integral of 1, and in fact, I'm going to split up my integral now. This is going to be the integral of 1 dx plus the integral of 11 halves to x minus 6, all divided by x squared minus 6x plus 16 dx plus the integral of, 14 over x squared minus 6x plus 16 dx. All right. And using some integral rules, this is the same thing. Well, first of all, I'm going to write an x right here plus the integral of, plus 11 halves times the integral of 2x minus 6 divided by x squared minus 6x plus 16 dx plus, I'm just going to call this, for shorthand, let's just call this squiggle, because we're going to worry about that one in a second. We want to tackle this guy right here. What I'm going to do here is, the genius of what I just did is I'm going to let u be the entire denominator. X squared minus 6x plus 16. Now, that tells me that du is the same thing as 2x minus 6 dx. Oh, but look at how powerful that is. I have 2x minus 6 dx sitting right here, and I have u being the same thing as x squared minus 6x plus 16 sitting in my denominator. So how does that transform my integral? What I have is, this is the same thing as x plus 11 halves times the integral of 1 over u du plus green squiggle. All right. Now, you might recall that we have an integral here, and I wonder if I want to spend time giving this spiel as of right now. We need to think of a function whose derivative is 1 over u du. And I can think of one, and that is the natural log. But as a quick explanation, this integrand right here has a domain of all real numbers other than 0, whereas our antiderivative will have a domain, if we're not careful, of all real numbers that are positive. The natural log only makes sense if the input is positive. But of course, if this is telling me the slope at all real numbers that would satisfy this domain, that's going to be all numbers other than 0. So that means my antiderivative has to make sense. This is telling me that the original function has a slope that makes sense for all real numbers other than 0. That tells me that my antiderivative has to make sense. It has to have a function value for all real numbers other than 0. And we fix that. So this is a loose, kind of quick explanation. But what I need is the natural log of the absolute value of u. Okay, so again, first of all, we thought to ourselves, what function has a derivative of 1 over u? The answer is the natural log of u. But this function has a domain of all non-zero real numbers, which means the antiderivative has to make sense. This slope function has a derivative of all non-zero real numbers, which means the antiderivative has to make sense for all non-zero real numbers. If we kept this natural log without the absolute values, then our antiderivative would unfortunately only make sense for all real numbers other than the negatives and 0. But we need it to make sense for all non-zero real numbers, so we include the absolute values. All right, I had to do a quick explanation of that guy right there. You know what? We're going to substitute u in right here, or maybe not yet. So this is the same thing as x plus 11 halves, the natural log of u. And reminding ourselves what this squiggle is, that's going to be 14 times the integral of 1 over x squared minus 6x plus 16 dx. All right, check this out. This is the same thing as x plus 11 halves, the natural log of the absolute value of u, plus 14 times the integral, watch me do this, this is the same thing as 1 over x squared minus 6x plus 9 plus 7. Okay, so why the heck did I do that? Here's why. I want to complete the square because this kind of looks like an arctangent. Natural log of the absolute value of u plus 14 times the integral of 1 over x minus 3 squared plus 7 du. All right, so in my head, here's what I have in my head. I'll kind of write it small. The derivative of arctangent of x is equal to 1 over 1 plus x squared. All right, that looks a lot like this thing in here. It's just that I have these random numbers involved. I have an x minus 3 in here and a 7 right here. But watch what I can do. I can force factor out a 7 from the denominator. All right, so you're like, well, what the heck does that mean? Watch this. 1 over 7 times, in parentheses, an x minus 3 squared. Here, let me write that better. An x minus 3 squared divided by 7 plus 1 du. Whoa. Sorry, dx. I messed that up. This should be a dx. All right, so this is, of course, the same thing as x plus 11 halves, the natural log of the absolute value of u, plus 2 times the integral of 1 over. All right, so I'm going to rewrite this part right here. I think another way to write that is x minus 3 divided by the square root of 7 squared plus 1 dx, and this is where the substitution is begging to happen. What I'm going to do is let z, or whatever the heck else you want, equal x minus 3 divided by the square root of 7. That tells me that dz is the same thing as 1 over root 7 dx, okay? And that tells me that root 7 dz is the same thing as dx. And look at what I have. Sitting right here, dx, I have another character for dx, that's root 7 dz. And sitting right here inside the square root, I have another another name for that, that is z. So how does this integral transform? What I have is this is the same thing as x plus 11 halves, the natural log of the absolute value of u, plus 2 times the integral of 1 over u squared. Sorry, not u. It's not u, it's z. We've already used u. Z squared plus 1. And then I'm going to replace dx here. dx is the same thing as root 7 dz. All right. This is the same thing as x plus 11 halves, the natural log of u, plus 2 root 7. Again, what I just did was I took this root 7 out of the integral. It's just a number after all. Times the integral of 1 over 1 plus z squared dz. All right, that's powerful because all of a sudden I can easily anti-differentiate. What we have is x plus 11 halves, the natural log of the absolute value of u, plus 2 root 7 times the arctangent of z plus c. All right. And like I said, I just gathered a whole bunch of constants in that final constant of integration. Now I do my substitutions. Notice that I have z right here. Another name for z is this thing right here. And way, way back here, I have the u. So I have u right here. Its original name was that polynomial that we started with. So substituting, this is the same thing as x plus 11 halves, the natural log of u, but that was x squared minus 6x. I think it was plus 16, plus 2 root 7 times the tan inverse, the arctangent of x minus 3 divided by the square root of 7 plus c. Everything's in terms of the same variable, and I'm good to go. All right, all of a sudden, like I said, we have bounds of integration. That means it's no longer find an antiderivative type of question. This is a find an area type of question. Let's dive in. My first guess is to let u be this denominator. Or, excuse me, the thing that's inside the square root in the denominator. That tells me that du is the same thing as 2 dx, but it also tells me, notice that this is a value in terms of x, so x is equal to 4. So if x is equal to 4, then what does u equal? Well, u is the same thing as 2 times 4 minus 6, and that is the same thing as 2, right? If x is equal to, I think it was 5, if x is equal to 5, that tells me that u is the same thing as 2 times 5 minus 6. That's the same thing as 4. So how does this integral transform? By the way, this one also tells me that 1/2 du is the same thing as dx. So let's see the pieces. What I have right here is dx, sitting right here. So another name for dx is 1/2 du. Oh, shoot. Immediate issue. I realize I am actually in a little bit of deep water, except I'm not. Because check this out, I can just isolate u. Adding 6 to both sides, dividing by 2, I get that u plus 6 divided by 2 is the same thing as x. All right, so what did I just accomplish? I have x right here. Another name for that thing is u plus 6 divided by 2. And this thing inside the radicand, or inside the radical, is the same thing as u. Okay, I just made a mess a little bit. But let's see how this transforms. And of course, I should mention this. I also discovered that that is going to get transformed to 2, right? Yeah, x equals 4 goes to 2. X equals 5 goes to 4. So this will transform to 4 in the u world. So how does this transform? What we get, this is the same thing as the integral from 2 to 4 of u plus 6 divided by 2 divided by the square root of u times 1/2 du. Taking the 1/4 out of the integral, we have 1/4 times the integral of, the integral from 2 to 4 of u plus 6 times u to the negative 1/2 du. This is the same thing as 1/4 times the integral from 2 to 4 of u to the 1/2 plus 6 times u to the negative 1/2. Grab some parentheses, du. Let's use that fundamental theorem. Let's skip calculating the limit of a Riemann sum. Let's be happy about it too. We have 1/4 times, we have 2/3 u to the 3/2 plus, okay, let me see if I get this right. 3 times u to the 1/2. We're going to evaluate this from 2 to 4. That was, of course, because of the... Oh, did I get that wrong? I think I did get that wrong. Yeah, that's not going to work at all. Hold on. I think it's 12. Yeah, 12. It should be 12. There you go. Because of the fundamental theorem of calculus. And this is the same thing, knowing our new notation. This is, first parentheses, I plug 4 in to use. So that's going to be 2/3. 4 to the 3/2 plus 12 times 4 to the 1/2 minus 2/3 2 to the 3/2 plus 12 times 2 to the 1/2, close parentheses. Okay, so let's simplify. I'll do this one. We have 1/4, 2/3. The square root of 4 is 2. 2 cubed. So again, the square root of 4 is 2. 2 cubed is 8. So 2/3 of 8. Plus, that's going to be 24. Minus, I don't think there's a nice way to do this one other than it's going to be 4/3 root 2 plus 12 root 2. So this is the same thing as 1/4. Let me close brackets here. 1/4, it's going to be 16/3 plus 72/3 minus 4 root 2/3 minus 36 root 2/3. That is the same thing as 4 plus too difficult. 23? No, is that right? 72 divided by 4. 18. Yeah. Boom. We just found the area. Fundamental theorem of calculus. Super powerful. Let's try another one. Oh, geez, what a mess. Actually, not too bad. I have t right here. I have actually 1 over t right here. And inside the sine function... Oh, shoot, it's sine squared. That's an issue. All right, we're going to have to take a side quest here, but that's all right. I'm going to let u be equal to the natural log of t. If t is equal to 1, what does that mean about u? U is equal to the natural log of 1, but we all know that that's the same thing as 0. If t is the same thing as e to the pi sixths, that implies that u is equal to the natural log of e to the pi sixths. And we all know that that's the same thing. The natural log and the exponential are inverse functions. So this is just pi sixths. And also we know that du is the same thing as 1 over t dt. So check this out. 1 over t dt. 1 over t dt. And I have u, natural log of t, sitting right here. And I can make these transformations on the bounds. Color code the whole thing. So this integral, that is the same thing as the integral from 0 to pi sixths of sine squared of u du. Again, that's because this thing is associated with the yellow. This right here is associated with the red. And of course, I switched the bounds associated with the blue. All right, so this is where I think I have to take a screeching halt, because we don't quite have a method. You might try a few things, like, I don't know, let u equals cosine or something like this. Let u equal sine. You're going to come into a little bit of an issue. But luckily, we know a little bit of trigonometry, and we remember that the cosine, this is going to seem random, but the cosine of 2 star is equal to the cosine squared of star minus the sine squared of star, right? But you know what? I want sine squared of star by itself. That tells me that sine squared of star is the same thing as the cosine squared of star minus the cosine of 2 star. Actually, you know what? Let me go back. That was probably the worst way to do this. Before I do that, I'm going to say that this is the same thing as 1 minus, here we go, sine squared of star minus sine squared of star. So again, this thing in blue, underlined in blue, we should remember from the Pythagorean identity, that is the same thing as cosine squared of star. So this is the same thing as 1 minus 2 times sine squared of that star, but that tells me, with a little bit of algebra, that sine squared of whatever is the same thing as 1 minus cosine of 2 star divided by 2. Okay, powerful. So what that means in my integral, this is the same thing, no calculus, 0 to pi sixths of 1 minus the cosine of 2u all divided by 2 du. That's powerful, because now what I'm going to do is let whatever I want, y equal 2u, so that dy is the same thing as 2 du, and if u is equal to 0, that implies that y is equal to 0. If u is equal to pi sixths, that implies that y is the same thing as pi thirds. All right, so how does this integral transform? This is the same thing as the integral from, or I'll write it like this, 1/2, taking this 1/2 out, the integral from 0 to pi thirds of 1 minus the cosine of y du, but du is the same thing as 1/2 dy. All right, so this is the same thing as 1/4 times the integral from 0 to pi thirds of 1 minus the cosine of y dy. And of course, that is a lot easier to anti-differentiate. This is the same thing as 1/4 times y minus the sine of y evaluated from 0 to pi thirds. That was, of course, because of the fundamental theorem of calculus. And that is the same thing as 1/4 times pi thirds minus the sine of pi thirds minus 0 minus the sine of 0. Oh, that's nice. And giving me a final answer, that's going to be, okay, so let's see. Pi thirds, or pi twelfths, minus, okay, sine of pi thirds, sine of pi thirds, it's the same thing as root 3 over 2, right? Yeah. Okay, so this is going to be root 3 over 8. Donezo. Last one. Oh, a few more. Shoot. That's all good. This is the same thing. Or excuse me, let's make a substitution here. This is a little bit tricky. You might be tempted to let the u be the entire denominator here, but you'll quickly find out that that's not going to work too well, because the derivative of the denominator is going to be 6x to the 5th power. All right. Now, what we can do, though, is rewrite this as the integral from 0 to 1 of 12x squared divided by 1 plus x cubed squared dx. All right, so the move I just made, that was purely algebraic, no calculus, because now all of a sudden I can let u be equal to x cubed, and that tells me that du is the same thing as 3x squared dx, and if u is equal to 0, that implies, if x is equal to 0, that implies that u is the same thing as 0 cubed, which is the same thing as 0. If x is equal to 1, that implies that u is the same thing as 1 cubed, which is the same thing as 1. And my entire integral can, of course, transform. My favorite way to say 12 is 4 times 3 check this out. There's my u. Here's my du. Including this piece right here. And of course I've switched the bounds properly. So this integral transforms. This is the integral from 0 to 1 of 4 divided by 1 plus u squared du. And that is the same thing as 4 times the arctangent of u from 0 to 1. Thank you, fundamental theorem of calculus. And oh man, what a stunning one. This is 4 times the arctangent of 1 minus the arctangent of 0. That's the same thing as 4 times pi fourths. That's the same thing as pi. Sheesh. I like that one. Man, my pen is all over the place. We got tiny integrals here, huge integrals. It's all good. All right, here we go. I have to find the area between two curves, but notice I have two functions. Oops. I have two functions that are in terms of y. Okay, so this is going to be a little bit of a pill. It's actually not too bad. It's not too bad at all. What I have to do simply is set these two things equal to each other so that I can find my bounds of integration. We're going to be integrating in the y direction. We are going to be stacking rectangles this way, right? And I simply need to know which one's bigger. Honestly, the picture kind of gives me this, but I think this one is more positive. What you could do is, well, first of all, we should find the bounds. That's associated with this guy right here. Notice it's more this way. And we have the red curve, which is going to be this one right here. It's a parabola, sideways parabola. And I want to find where where the yellow curve meets the red curve. So let's do that. I'll have 1/9 y squared is equal to, oh geez, 5y. This is going to be disastrous. 3 times the square root of 16 plus y squared. It might not be that bad. That tells me that I'll go with 3 times the square root of 16. Oh, no, I'll do it like this. 3y squared times the square root of 16 plus y squared. Well, first of all, these curves are the same at 0. That's obvious from the picture and this equation right here. And this is going to be equal to 45y. And what I could do is cancel one of these y's as long as y does not equal 0. That makes my job a little bit easier because I see that point already. So I want to find a different point. That point's right here. I want to find a different point. And I could do that by, oh geez, do I really got to do this? Squaring both sides? No, don't do that yet. Divide both sides by 3 first. So y times the square root of 16 plus y squared. That's going to be equal to 15y as long as 3 does not equal 0. And that tells me that, oh, sorry, not even 15y. Oh, blunder, just 15. Okay, now I can square both sides. We have y squared times 16 plus y squared is equal to 225. That tells me, oh shoot, hopefully this turns out nicer than it seems like it's going to be. Y to the 4th power plus 16y squared minus 225 is the same thing as 0. And yeah, I think we got this. This is the same thing as y squared. Maybe we got this plus 25? Y squared minus 9 equal to 0? Is that going to work? Yeah, Yeah, that'll do. All right, so that tells me that y is the same thing as plus or minus 3. At least in the real world it is. And just by staring at the curve, this one is certainly going to be a y value of 3. To find the x value, honestly, I don't need the x value, but what I could do is simply plug y equals 3 into this equation, and that'll give me an x value of 1. But I don't need that x value. Remember, we're stacking rectangles in the y direction, which means I'm going to start here at y equals 0 and stack up to here, and that is y equals 3. And I have this integral, the integral from 0 to 3. I want the bigger function first, then take off the smaller function. All right. That is going to be this guy. This is the same thing as the integral. So again, the bigger function, or perhaps better said, would be the more positive function minus the other function. This is going to be the integral. From 0 to 3 of 5y divided by 3 times the square root of 16 plus y squared minus 1/9 y squared. And both of these are not too bad, but that will get you the exact blue area given right here. And I'm going to leave the video there. Do this integral as homework. I'm almost at 1 hour on the video, and I want to keep it under.